Hi, good morning, and welcome to the ZP Developer Zone. So we like to do this Developer Zone sometimes once or sometimes twice a week, really just answering questions that have come in from the sort of biosensor development community. So let me jump straight into it and try and be efficient with the time. So today's 31st of March 2024, and the questions that we're going to answer today is about making a low-cost IVD, that's a low-cost in vitro diagnostic. Somebody wants to ask what the smallest possible resolution is. And the quick answer to your question is, I realized whilst answering one of the first questions here that you're actually doing impedance spectroscopy. And actually, I think your question becomes a sort of moot point once you realize that actually you could do very good impedance spectroscopy on screen printed electrodes. So I will address that. Question here, sensors are properly calibrated. This is really a manufacturing issue. And it's something that you really either solve by using materials from people like Zimmer and Peacock, or you unfortunately have to get enough funding that you can put a quality system in place to make sure that you don't have issues of sensors not being calibrated. It's interesting actually because they mentioned that electrodes might get chipped off. So I got a suspicion, I'd never spoken to this person directly, but I have a suspicion that you may have gold on glass. That does tend to chip off a lot. So avoid those gold electrodes on glass if that's what you're using. Normalize signal to minimize inter-cartridge variability. Again, this is really a manufacturing issue. So I mean, at Zimmer and Peacock, we have customers on the market with microfluidic cartridges. Those customers are CE marked, and approved for clinical use. And it's just about, having control of your manufacturing. But I will discuss it. And final sample measurement. We're actually doing tests on sensors where the test volumes in actual products are like more like 1 microliter or 4 microliters. But just understand that most of the academic literature on electrochemistry is really imagining an infinite reservoir. So in fact, you will have, I don't want to call them problems, I want to call probably challenges or interesting challenges when you try to reduce the volume. But typically a glucose sensor is working with a volume of 300 nanoliters. Zimmer and Peacock, just historical. We've often working in microfluidic devices where the volume being tested is 1 or 4 microliters. Especially if you're doing molecular assays, it's probably a good idea to reduce the sample volume because you reduce the cost of expensive materials. Anyway, I'll get to those questions as I go through today. Question number 2, somebody's having a lactate sensor problem. Which is interesting because I was just reading your question just slightly more now, and I realised actually the sensors have come back to ZP. We've tested them and then we've sent them back again. But anyway, I'll talk and walk through that today. So question number 1, I should actually say 2 upcoming webinars, and we do say this in our weekly webinars, but there's a demonstration of a technology platform to get people to market very rapidly, and I realised that actually. In question number 1 today, they're asking about electrodes with a very fine resolution. I'm going to answer the question by saying, actually, I think you could just use screen printed gold electrodes, and I won't just say it, I will prove it using our own data. So if you go that direction, you can have at least an early proof of concept in front of investors and clients very quickly, because actually be able to use this platform. And on the 23rd of April, there's one in the morning, one in the afternoon. These webinars are not static. We're always updating with new material, so please come to one in the morning, one in the afternoon. If you're more on the academic side of things, you're not so interested in the commercialization of electrochemical biosensors, then we have a different webinar, a different day, one in the morning, one in the afternoon. They are basically repeats of one another, but they're just so that people in different time zones can attend. We tend to find that sort of Canada, USA, Mexico, the South American countries tend to come in the afternoon, and the morning sessions tend to be Asia and Europe. That said, question number 1, what's the smallest resolution? I'm guessing the size of that we can achieve is like 200 plus microns or so. I think that's a fair comment. The reason being is not that we couldn't go smaller. The reason being is it's manufacturing repeatability. I mean, there are some interdigitated electrodes out there that have very fine resolution, but they're quite expensive, and they're actually they're quite expensive, and they've been around for quite a few years, but there's actually no commercial exploitation of them apart from into the R&D market. So you've really got to think through this resolution part, because having features that are very small like this is giving you a cost, and it will also end up giving you a yield problem. And then I hadn't read the rest of your questions when I was thinking this through a little bit, and then I realized why. Why are we doing this? And then I kind of thought, oh well, I bet it's because they're doing impedance spectroscopy. And then I thought I'd show you this data that actually this is an EIS assay, an electrochemical impedance spectroscopy done on a ZP gold electrode. It's a kind of an immunoassay type application where we have an antibody that's capturing an antigen, and we're detecting that binding by having a redox label in the solution. So the question whether ZP can do 100, 200, 300, 400 micron resolution electrodes. I'd actually say the larger you make them, the higher your yield and the better your quality. And then the question why, and when it occurred to me, it's because they're doing EIS, electrochemical impedance spectroscopy. And then I thought, well, actually, you don't need to be doing EIS. In fact, here's a link to some data that we have on our website demonstrating that ZP was more than capable of making EIS and measurements on a bioassay using gold electrodes. So hopefully that's useful to you. So I'd actually rethink this through a little bit, because obviously the list of questions you have tells me that you do have a bit of a problem with the electrodes, and I think you maybe want to try a different platform. And therefore I linked to the gold electrodes as well. This person has kind of essentially, if you want to stick with gold, you have two options. You can have thick or thin gold. I think you're already using thin gold, but you haven't tried thick gold. Actually, we have used thick gold or screen printed gold in EIS quite a lot. If you go for thin gold, admittedly, yes, we can. We're better at doing customization in thin gold, because actually we can start with this kind of square that's 50 millimeters. The pixels within this square are 250 microns. So you're correct. When you said in your question one, what's the kind of resolution of features you can make? Is it 200 plus? And you're right, it's 250 microns would be a fair way of looking at this. It could possibly come down. But once you get smaller, then you'll get into a yield issue. A lot of your questions are really about quality. And actually, one of the effects on quality is the smaller you make something, the harder it is to basically make it. So I'd actually suggest you didn't keep going small, and actually I would rethink this a little bit. But that said, we can make feature sizes in gold using this sputtering technique down to about 250 micrometers. And I know that you've seen these slides before, so I won't dwell on them too much. But I do want to say to anyone else that there will be some links to what these slides mean and the way we can actually make custom gold electrodes at ZP using this kind of technology. I would strongly suggest, and I've linked to it already, that you actually try out these hyper-value gold electrodes. Why? Because we use them all the time in EIS, electrochemical impedance spectroscopy assays. The biggest user of ZP gold electrodes is simply ZP. What do we use our gold electrodes for? Mostly for building self-assembled monolayers, where we put on either a molecular assay, like a sort of a 20 mer, which is a 20 strand of DNA for capturing another piece of DNA, or we put an antibody on there for capturing proteins, for example. So these gold electrodes are something we use a lot. I would also strongly, you start your questions with low cost. Gold is not low cost. The only reason people use gold is because of the self-assembled monolayer chemistry that kind of works very well. But gold's been getting more and more expensive over the years. In fact, I was showing on the previous slide, unfortunately, gold now has got to a point where 100 screen printed electrodes of ZP was something like 800 euros. And I appreciate, that doesn't help you on the journey to low cost. But here are 300 screen printed electrodes, same quality, but it's in carbon for 269 euros. So you can see, that we're essentially a tenth the cost when you go to carbon. And we also have a 501 as well, which is sometimes easy to use because you can pipette onto it. Now I've linked both of those here. And I also have a paper here where we use differential pulse voltammetry to measure a immunoassay. I would say that square wave voltammetry, differential pulse voltammetry, and EIS, electrochemical impedance spectroscopy, they all get you to a really similar place. If you're trying to make a sort of binding type assay where you have something on the surface and something specifically binds to it, and that's the source of your signal, then I would say differential pulse and square wave voltammetry are good. The way we tend to do it at ZP, we will have a surface with a binding material on it, something that's bound, something that then gets bound to it, and then we'll have a redox reporter in the solution. In the paper here, I think they use ferricyanide. They have a redox reporter that's trying to get to the surface, and its ability to reach the surface gets impeded by the binding to the surface. But I actually got some slides on that anyway. So it's just a side note. First of all, I can understand why you want the 100 micron resolution, because you're doing, now I understand, impedance spectroscopy on interdigitated electrode. I have demonstrated to you, in fact, you don't have to do impedance spectroscopy on a interdigitated electrode. This is a kind of, it's just a hang up in the literature. And I actually think, I'm not even sure the literature that's saying this is that modern these days. So you can actually use a gold screen-printed electrode already. Those are easier to manufacture. And now I'm saying actually don't even need to use gold, you can use carbon. You take the carbon electrode, you put pyrene NHS. By the way, I'll put a link to the paper as well underneath the slides. With pyrene NHS, it's got a click chemistry. You can bind your material to the surface. I understand if you're doing sort of thiol coupling, you may want to think this through a bit, but it doesn't break the idea that actually carbon is 1/10 the cost of gold. And it's just, if you're looking for low cost IVD, then carbon is your material. I think we block the surface here with chitosan. We do follow the process using cyclovoltammetry. So we start with a pristine electrode, and as we functionalize the surface, we follow the cyclovoltammetry accordingly. And then we test, as I say, we use differential pulse voltammetry, but I think EIS would have worked just as well in this case, but it was differential pulse. Square wave would have also worked just as well. And as the surface is blocked, the magnitude of this signal increases. I explained this in the paper, but this is actually counterintuitive because it's acting like a blocking assay, but in fact the signal goes up. But I've realized over the years not to worry about this, not to worry about this sometimes. I mean, I did explain it that it's due to an electrostatic change, and I explained it actually in the paper. I remember I wrote the paragraph on that. So my advice so far is, yes, we probably wouldn't want to do your 100 micron electrode. Why? Because you're already, I don't want to say struggling, but I feel like from the correspondence we've had that, you know, if it was working well, you wouldn't necessarily be asking the questions, but it's not. I think trying to do it at 100 micrometer gold is affecting a lot of your questions are around quality. I suspect that that's the source of your quality. My quick advice is try out screen printed gold. You can follow our links and see that actually, you know, this is not just a comment, this is a reality. And then you can actually also try carbon as well. Why? Because you want to be commercial. If you want to be commercial, you have to have a low cost of goods going in. Otherwise, all your products are going to end up being expensive. So this paper is probably worth reading. A lot of your comments are really around quality and around repeatability. So if you're using ZP screen printed electrodes, we check the quality before we ship. And you've been to our webinar, so I won't overplay that. But if anyone else is interested in the reproducibility of ZP screen printed electrodes, then please click this link as number 2. How are sensors properly calibrated? This is critical in a business setting. Let's say if part of the electrode was chipped off during manufacturing, chipped off during manufacturing merely makes me think that you may be doing, you've got some sort of product that is possibly a glass substrate at the moment, and you're vapor depositing gold onto it. And I do find those types of devices quite fragile, and that kind of chipping of a screen printed electrode, I don't want to say it never happens, but certainly not on the standard materials that we have at ZP. It's just not something that we see. So this is really this is a kind of problem, or possibly of where you're at today. I have done a video on this on technology readiness levels, manufacturing readiness, and application readiness level. So I will put a link to that. The reason I bring that up is because when you're asking about things chipping off during manufacturing, it sort of says, look, you know, maybe you're at manufacturing readiness level number 3, and actually, you know, you need to get to manufacturing readiness level number 9. There's not a well, there's an easy fix to your problem, I suggest, and that's to start using either ZP screen printed gold electrodes or ZP screen printed carbon electrodes. That's the easy fix. Otherwise, you know, it sounds like you're at manufacturing readiness level number 3, and you'll have to get to manufacturing readiness level number 9, and that's, you know, that's just part of the course of trying to make a commercial sensor. I want to talk about risk and cost here, because I got a suspicion that if you go on the route of bespoke electrodes, you're effectively at, I would call, manufacturing readiness level 1. This is the highest cost and highest risk. You're going to have to build a sensor, get the supply chain going, sort out things like chipping and repeatability. I mean, ZP's been around for 10 years, and so we've spent that sort of 10 years actually getting our, let's say, screen printed electrodes to manufacturing readiness level number 9. But that is, you know, I can easily say, you know, if ZP's kind of, you know, in the early days, you know, it's a sort of 2 million revenue per annum. You know, this is over 20 million spent to get to these kind of manufacturing readiness levels number 9. So when you hear about companies getting investment, it's because, you know, in order to make a reproducible substrate, which is just the start of your journey, which is, I would say, you know, manufacturing readiness level number 9, ZP spent a long time getting there. So when you start with bespoke in your question, then you are really starting at manufacturing readiness level number 1, which is just really an idea, and you have to lift it up to number 9. So if you've got problems like chipping, I've got to say, that's not something that happens so much with ZP screen printed electrodes, probably because of the material choices. And if you stay on the route that you're on, you're just going to have to get better with manufacturing, but that's, you know, a long decades journey. In fact, it's something I talk about sometimes in those webinars where I say, you know, people spend 5, 10, 15 years trying to make their product, let's say, and at the end of it, only 10% of companies are successful, because often they get tied up in problems like this, of, you know, just reproducibility on the cartridge. In fact, I can think of a company that went into liquidation in the UK just recently, where it was manufacturing repeatability that really killed them. And this is really manufacturing repeatability as well, that they make up cartridges, and they basically have to do a calibration on the cartridge in order to normalize the signal when they actually put a real sample on there. And this really comes from, so this is kind of in-field calibration normalization. You see this a lot in the academic literature. And the reason you see it a lot in the academic literature is because of manufacturing repeatability, that if you could control all your variables, then you would have a repeatable product. In fact, I will show a product in a minute where, you know, making it repeatable, and we've been making it for probably over 5 years at this point. That's been one of the big things we've done. So your irreproducibility is due to electrode variability, I suspect, times your electrode functionality. I suspect that you're functionalizing the electrode in some way. I suspect that's a source of variation. You've got your cartridge itself, your walls and height of your cartridges repeatable, and then your cartridge assembly, the way you put it together, maybe it's not repeatable. So all these things stack on top of each other, and you end up then with an IVD and in vitro diagnostic that's not necessarily repeatable. No criticism of you, it's just you're possibly at manufacturing readiness level number 3 and you need to raise to 9. ZP does this all the time. This is part of our contract development, contract manufacturing, but you have to recognize where you're at. I would say you could at least improve the first part, which is electrode variability, by getting ZP's electrodes. You will notice that, you know, I emphasize it in our webinars that, you know, these are all triplicate data. I mean, admittedly, the signal's very high. I've got a suspicion that your signal's much lower, but these are triplicates, you know, and they reflect on the underlying repeatability of our screen printed electrodes. But I have said that in the past. Question number 1D is really about the volume that we may put above an assay. So this is it's actually a microfluidic cartridge in here. I might rewind for a second and just pause here. This is a microfluidic cartridge. Here you can almost see the connections from a ZP screen printed electrode. So you can see a ZP screen printed electrode within a microfluidic cartridge. And the typical kind of volumes that we may be using in these kind of devices is 1 or 4 microliters. the equations that people rely on to understand electrochemistry are really built for often infinite sample sizes. So 50 microliters, a lot of the time, depending on your electrode size, does feel like to the electrode like a fairly large reservoir. So it kind of works. So if, we can put 50 microliters on there and we can do fairly standard chemistry. Once you get into the microfluidic chambers, where you may be talking about more like 1 or 4 microliters, then some of those equations or some of those assumptions actually start breaking down. Now at ZP, I think there are very few, let's say, teams out there that possibly understand electrochemistry and microfluidics quite well, but at ZP we definitely do. And I was able to adjust, let's say, the assay to take a care of the microfluidic environment. But just FYI, if we were putting our screen-printed electrodes into a microfluidic cartridge, we would expect much lower volumes, and we would also expect that the signal would be changed. In fact, we have a client at the moment who we are moving their electrodes into a microfluidic environment, and we have, we've got a risk register. We said this is a risk because all the testing that you've been doing, let's say, in open droplets, we can take lessons from it, but it's not just a one-to-one translation. We do actually, we do have to do a bit of a translation of what we did here to what we do in the microfluidics region, so be careful. It's probably worth saying that at ZP we have fully functionalized labs, we have ISO 13485, we have contract manufacturing, contract development, so people are very welcome to contract us because, like I say, I think the success rate of most startups is basically 10%. I wonder if it's even lower in the deep tech like that biosensors falls into. So I think people do need advice earlier on, otherwise they're going to unfortunately repeat the mistakes of the past. Question number 2, somebody's got a problem with their lactate sensors. I got a suspicion they've actually got a problem with the instruments, so we're going to have to take a look at this. But when I look at their lactate sensor, it's meant to be running in an amperometric mode. So I kind of, this looks flatline to me. Flatline means there's some sort of breakage on the counter electrode. When I say breakage, I think electronically, which makes a bit of sense actually, because they're using a potassium sensor from us, so they're getting pretty good results. But I realize that those potassium sensors are using the working and reference electrodes, so it would make sense then that they went to amperometric mode and it was a counter electrode. That was the problem. They sent me images. I can't physically see that there's anything particularly wrong with it. And in fact, I'm even looking at their settings for this lactate sensor, so the settings all look good. I really can't. So how do we do it? Well, they are a paying customer, so therefore we'll get online with them and give them support because we know what we're expecting, but they're not getting it. But the nice thing about doing these webinars is when you think about, well, they're using these electronics and it works well on the potassium sensor, which is an ion selective electrode, which is a open circuit potential measurement, which actually uses the reference and working, and then they try to do a different type of assay, which is amperometric, where the counter is included. And I had an intuition that there's something wrong on not the sensor, but the electronics, and we'll take a look at that with them. So making a low-cost IVD, that's critical, that word there, making it low cost. Low cost, you've got to be really careful with being bespoke too early on with low cost. If you're bespoke very early on, you're carrying all the costs of production on your product. Whereas if you take a off-the-shelf screen-printed electrode from something like ZP, then actually you don't have all of the cost of producing that electrode on you. So when you're at low volume, it doesn't mean that you have necessarily high costs. So for example, screen-printed carbon electrodes from ZP, if you buy them in very small bulk, they're 80 cents each. So that would allow you to get IVD. The reason you're asking for small resolution is because I think you have a background in electrochemical impedance spectroscopy, where there's a sort of interdigitated electrode movements, but in fact you don't need interdigitated electrodes to get perfectly good impedance spectroscopy in the biosensor world. Sensors are properly calibrated. You're either working with an ISO 13485 contract development, contract manufacturer like ZP, and you have a budget for them, or the chipping that you described in particular sounds like a materials problem between glass and vapor deposited gold. You cannot do you cannot do calibration as you describe in the field. It will just burden your problem with costs, and it will really affect the usability. So at ZP, There's a video that that's linked to in this slide deck. You won't see us do a in situ calibration on a medical product like that. We may do it in the early days. So let's say we were doing early clinical studies with the hospital. We may do a in situ calibration, but we wouldn't actually go to market or do an FDA submission with an in situ calibration as you described. It's just going to really mess up the user experience and be a big source of error because you're expecting nurses and clinicians to do that calibration. They can't do it. Well, they can do it. They don't have the time. Final sample measurement. Microfluidics will affect your signals and assumptions that come from the macro world of electrochemistry. At ZP, we have dealt with this in the past. This lactate sensor, I've got a suspicion it's not the sensor. I think the suspicion there's a problem on the line of the counter electrode. But I think it just demonstrates that ZP, we do understand, let's say, electrochemical biosensors at lots of levels. So I want to say thank you. If you've got any questions, don't hesitate to reach out to us. Okay, thanks very much.